Good morning children, stay safely at home. So I am starting the next topic of this chapter, that is we already studied in the previous lecture that what is linear expansion and what is the coefficient of linear expansion. So what is the concept of linear expansion? Whenever we heat a body, on heating the body, there will be a change in length of the body, that is known as linear expansion. Alright, and we have got this also, coefficient of linear expansion. It is given by change in length by original length into change in temperature. Alright, now here experimentally with the help of an activity you can demonstrate it. So for that what you need? You need the wooden stand. This is the L-like structure and there are two fixed wooden stand M and N. Now over that fixed wooden stand you keep a solid rod. You keep the solid rod in such a manner that it is touching this rigid support at the point A, and this point B it is free. Alright, it is touching the pointer here. It is touching a suspended pointer. Alright, now the pointer, it can move over a scale. So what you see, this was the first initial length. This point B, it was the initial length of the rod and the pointer was like this. Now you do one thing, in between the two support M and N, you keep one Bunsen burner and by the burner you hit the rod. Then you will see that if you hit the rod for some time, then this length, this end, it will increase, that this end will move. Why? Because you see this end, it is fixed to the rigid support. So it cannot expand. The rod cannot expand in this direction. So what will happen? The rod will expand in this direction. You see this is this portion. This portion is the extended part. So what the extended rod is doing, pushing the pointer, and you see the pointer is moving on the scale. So from the scale you can find out what will be the amount of linear expansion. You can see that more heat you will give, more will be the linear expansion. So this is the way you can demonstrate by a simple experiment that the linear expansion in solid on heating. Now next topic is superficial expansion. So what is superficial expansion? The change in the surface area of a body on heating is known as the superficial expansion. So just like the linear expansion, superficial expansion also depends on initial area of the body. Or the solid. Greater the initial area, greater will be the superficial expansion. Means what? Suppose you have taken, one girl has taken this area, a small area, alright, this, and the material is same. Suppose you have taken copper. Another girl has taken a bigger area. This is the bigger area. Now you hit it. Then you will see this will expand less, but this will expand by more amount. Look at this. This is more amount and this is less amount. Okay. This is the meaning that greater the initial area, greater is the superficial expansion. The diagram you don't have to draw. Now the second factor on which the superficial expansion depends is change in temperature of the solid. From your common sense only you can make out that more the change in temperature, greater the change in temperature, greater will be the superficial expansion. Just consider this example. Suppose two girls have taken two plates of same area and both are made up of copper. Now one has increased the temperature, suppose increase the temperature from 20 to 40 degrees Celsius, another has increased the temperature from 20 to 100 degrees Celsius. Then you will see in the first case the change in temperature is 20 degrees Celsius, in the second case change in temperature is 80 degrees Celsius. So in the first case expansion will be less and in the second case expansion will be more. Alright, so greater the change in temperature, greater is the superficial expansion. No need to draw the diagram. Now next factor on which superficial expansion depends is nature of material of the solid. Just you consider this example that suppose you have two girls have taken two plates. One is made up of brass, another is made up of iron. Their initial area is same and both of them are increasing the temperature by the same amount. means from 20 to 40 degrees Celsius as for example. Alright. Then you will see that brass will expand more than iron. Why? In this case you see initial area is same, change in temperature is same, but as materials are different, the amount of expansion will be different. Brass will expand more than iron. Alright. So superficial expansion depends on three factors: initial area of the solid, change in temperature of the solid, and nature of material of. Now let us concentrate on the mathematical formula. So if you consider that at 0 degree Celsius, let the area of the solid be S1, and at T degree Celsius, area of the solid become S2. Means area increases from S1 to S2. So you see what is the amount of superficial expansion. Superficial expansion is equal to S2 minus S1. Alright. Now according to our concept, what we have got, S2 minus S1 directly proportional to S1. It is initial area, and then S2 minus S1 is proportional to change in temperature. So how much is the change in temperature? T minus 0, that is T. So if you combine these two, you can write S2 minus S1 proportional to S1 into T. So you see, you can write S2 minus S1 proportional sign. When you will replace by an equal sign, you have to write here a constant of proportionality. So that constant of proportionality is beta. I have written here beta. So this beta, this is a Greek letter. I hope you know how to write, and you have observed also how I have written beta. And beta is known as coefficient of superficial expansion. What is the name of beta? Coefficient of superficial expansion. So you see, beta you can write it as S2 minus S1 by S1 into T. Means beta is equal to change in area divided by initial area into change in temperature. Alright. Please you write down properly, because whatever I am writing, if it is not visible, then verbally also I am saying. So if you listen to the lecture, then you don't have to ask me in message that what is written. Okay? Because if you listen to the lecture, then everything I am saying verbally also. So what is beta here? Coefficient of superficial expansion. Coefficient of superficial expansion is equal to S2 minus S1 by S1 into T. So S2 minus S1 is change in area, S1 is initial area into T is change in temperature. So in this case also you see what will be the SI unit of beta. SI unit of beta, you see change in area is meter square. Again initial area is also meter square, and then change in temperature you can write Kelvin or degree Celsius. So what it is coming, either Kelvin to the power minus 1 or degree Celsius to the power minus 1. So what is the SI unit of beta? Just like alpha, coefficient of linear expansion, SI unit of beta is per Kelvin or per degree Celsius. Now next is cubical expansion. So cubical term is associated with the volume. So what is cubical expansion? The increase in the volume of a solid is known as the cubical expansion. So just like the linear expansion and superficial expansion, cubical expansion also depends on initial volume of the solid. How does it depend? Greater the initial volume, greater is the cubical expansion. Cubical expansion depends on change in temperature also. How does it depend? Greater the change in temperature, greater is the cubical expansion. It also depends on nature of the material of the solid. For different materials, cubical expansions are different. So I hope you have observed that linear expansion, superficial expansion, cubical expansion, almost they are same. Only thing is linear expansion is change in length and superficial expansion is change in area, whereas cubical expansion is change in volume. Now if you consider the mathematical relation, then if I consider V1 be the volume of solid at 0 degrees Celsius and V2 be the volume of the solid at T degrees Celsius. So V2 is greater than V1. So what is the cubical expansion? V2 minus V1. So again you can write just like the linear and superficial expansion. V2 minus V1 is directly proportional to the initial volume V1. Then V2 minus V1 is directly proportional to the change in temperature T. So if you combine both the relations, you can write it is V1 into T. V2 minus V1 is proportional to V1 into T. So you can write V2 minus V1 is equal to some constant into T. So this constant is denoted by gamma and it is known as coefficient of cubical expansion. Gamma is known as coefficient of cubical expansion. Alright, so you see you can write what is gamma. Gamma is equal to V2 minus V1 by V1 into T. So you can write gamma is equal to change in volume divided by original volume or the initial volume into change in temperature. Alright, now what is the SI unit? SI unit of gamma. Now you know what is the SI unit of volume, meter cube, initial volume meter cube, then change in temperature you can write it as Kelvin or degree Celsius. So again meter cube cancel. So what is the SI unit of gamma? Per Kelvin or per degree Celsius. Alright, so these are the important mathematical relations related with gamma. So we have got three coefficients of expansion: alpha, coefficient of linear expansion; beta, coefficient of superficial expansion; and gamma is the coefficient of cubical expansion. Now they are interrelated. What is the relation? Alpha is equal to beta by 2 equal to gamma by 3. This is one of the way to write their relation. Or you can write this way, that alpha is to beta is to gamma is equal to 1 is to 2 is to 3. Both the form you must learn and remember. Okay, so these are the relations between alpha, beta and gamma. So already I have discussed experimentally how you can demonstrate the linear expansion of a solid. Now let us find out how to show superficial expansion of solid. So for that you just take a metal sheet. Suppose you have taken a metallic sheet and then by a iron nail you make a hole in the metal sheet. Okay, and then you see the iron nail, it will be, if you just fix it, then the iron nail will be like this. It will be just exactly fit in the hole. Okay, now you do this. You take out the iron nail, alright, and then you place the metal sheet on a Bunsen burner in such a manner that Bunsen burner heats up this region, the region near the hole. Okay, you just heat up the metal sheet near the hole for a longer time. Then after that you just insert the nail again. You will see the nail now in the second case, after heating through the hot metal sheet, the nail will pass through the hole and it will fall down. Okay, so this explains that when you are heating, then what is happening, the size of the hole is increasing and the metal, the iron nail can pass through it very easily. So this is the experimental demonstration of superficial expansion of. Next is, if you want to demonstrate cubical expansion of solid experimentally, then these are the apparatus you need. There is a stand and clamp here. You see there is a stand, and with the stand a ring is connected. A metallic ring is connected, and from the stand here there is a hook like structure. From that you can suspend one solid metallic ball. Now the size of the metallic ball when it is cold, it is such that it can pass through the ring. Alright, means if this is the ring, then the metal, this one, the solid ball, it can pass through it when it is cold. Now you do it, that you heat up this one, heat up the ball, heat up the solid ball, not the ring. You heat up the solid ball separately and now you put it on the ring. Then you will see that it will not be able to pass through the ring as it is done when it was cold. What does it mean? That when you have heated the ball, the size of the ball has increased. So that's why it is unable to pass through the ring. So this is the simple experiment by which you can demonstrate the cubical expansion of solid. So we have learnt about the expansion of solid. Alright. Now next is, what about the thermal expansion of liquid? And you know that liquid do not have any definite shape. If you keep it any container, it just take the shape of that container. And liquid you cannot, liquid do not have, that's why, any length, area. It has only volume. Alright. So whenever we consider the thermal expansion of thermal expansion of liquid, unlike solid, we do not have three types of expansion: linear, superficial and cubical. The liquid always have only cubical expansion, expansion in its volume. Now if you consider all the liquid except water, then you will see that if you increase the temperature, means on heating, the volume of the liquid increases. Alright, but for water the fact is very interesting. If you increase the temperature from 0 degree to 4 degrees Celsius, from 0 degree to 4 degrees Celsius, volume decreases. Alright, what we know that if we increase the temperature, volume increases, isn't it? But in case of water, what happens? From 0 degrees Celsius to 4 degrees Celsius, if you increase, you just look at the arrow, 0 to 4 I have given. What does it mean? You are increasing the temperature from 0 to 4 degrees Celsius, then what will happen? Volume will decrease. Alright, so you see, you can say that the water expands on cooling. Alright, from 4 degrees Celsius to 0 degree Celsius. Clear? Means if you cool down water from 4 degree to 0 degree Celsius, then only water will expand. But if you heat up from 0 to 4 degrees Celsius, then what will happen? Water will not expand. Water will contract. The volume will decrease. Alright. So the expansion of water on cooling from 4 degree to 0 degree Celsius. So let me rewrite it. So the expansion of water on cooling it from 4 degrees Celsius to 0 degrees Celsius is known as anomalous expansion. So you must learn the definition of the anomalous expansion because it is a very important term. Okay, so what we have learned about the expansion of liquid, that all the other liquid except water, on heating, volume increases, it expands. But in case of water, what happens? From 0 degrees Celsius to 4 degrees Celsius, on heating, water contracts. But on cooling, from 4 degree to 0 degree Celsius, water expand. And this expansion of water on cooling it from 4 degree to 0 degree Celsius is known as anomalous expansion. So if you consider the water that it is heated from 4 degrees Celsius to above, means anyone, then what will happen? Water expands, means volume of water increases, or you can write volume of water increases. So water behaves like normal liquid after 4 degrees Celsius, but below 4 degrees Celsius it behaves in a different way. So that point you have to remember. And remember that for different liquid, the amount of expansion will be different. Next is thermal expansion of gases. Now what happens in case of gas? gas, if you increase the temperature, and gas also just like liquid, it is also not having any shape, and gas do not have any volume also. Alright, means if you take a small container and if you take certain amount of gas, you can fill it up. Thus, and if you take a bigger container and you can fill up that bigger container with the same amount of gas also. So gas do not have a fixed volume. So in case of thermal expansion of gas, if you increase the temperature, then gas expands, and remember that expansion of gas is much higher than that of liquid, and expansion of liquid is greater than that in solid. Why it happens? Because coefficient of expansion for gas is much bigger than coefficient of expansion of liquid, and it is bigger than coefficient of cubical expansion for solid. Okay, gamma of gas is greater than gamma of liquid, greater than gamma of solid. So if you compare now the expansion of solid, liquid and gas, how you can write down? Solid may have linear expansion, superficial expansion, cubical expansion. Liquid is having only cubical expansion. Gas is also having only cubical expansion. Alright, and then the second point of difference you can write that cubical expansion of gas is maximum, whereas cubical expansion of solid is minimum, and cubical expansion of liquid is moderate. Means cubical expansion of liquid is greater than that in solid but less than that in gas. So these are all about the thermal expansion of solid, liquid and gas. Thank you girls.